In this lecture, we'll look at how to verify platform binaries before deploying a cluster. The Kubernetes platform binaries are available at the Kubernetes GitHub release page. It is important to verify that the downloaded binaries are safe to use by comparing against the checksum hash found against each binary within this page. So these binaries are served on the internet, so when you download the binaries, they are downloaded from the hosted servers to your system. Now, it is possible that an attacker who may have gained access to either your network or somewhere in between can intercept your download request and return his or her own version of the file, which may contain malicious code. Now, this may go unnoticed if the downloaded file is not verified against the checksum. Each file has a unique checksum or hash, and the smallest change in the file will generate a completely different hash. So it is important that all downloaded files are verified against the hash available on the download page. So here we run the curl command to download the Kubernetes binary, and then we use the SHA-SUM command line utility to generate our own hash of the downloaded file. We then verify the output of our command against the one that is available in the release page, and we make sure that they are exactly the same. In this case, we see that it's exactly the same. Note that the commands are different on different systems. On Mac OS, use the SHA-SUM command with the -A option to specify 512 or 256 bits. And on Linux, use the SHA-512-SUM command to generate a 512-bit hash of the file. Well, in the upcoming labs, you will walk through how to download and verify Kubernetes binaries using these commands. And I will see you in the next one. Hello and welcome to this lecture. In this lecture, we will discuss about the various Kubernetes releases and versions. So what do we know about API versions in Kubernetes so far? We know that when we install a Kubernetes cluster, we install a specific version of Kubernetes. We can see that when we run the kubectl get nodes command. In this case, it's version 1.11.3. In this lecture, we will see how Kubernetes project manages these software releases. Let's take a closer look at that version number. The Kubernetes release versions consist of three parts. The first is the major version, followed by the minor version, and then the patch version. While minor versions are released every few months with new features and functionalities, patches are released more often with critical bug fixes. Just like many other popular applications out there, Kubernetes follows a standard software release versioning procedure. Every few months, it comes out with new features and functionalities through a minor release. The first major version, 1.0, was released in July of 2015. As of this recording, the latest stable version is 1.13.0. Whatever we have seen here are stable releases of Kubernetes. Apart from these, you will also see alpha and beta releases. All the bug fixes and improvements first go into an alpha release tagged alpha. In this release, the features are disabled by default and may be buggy. Then from there, they make their way to beta release, where the code is well tested, the new features are enabled by default, and finally, they make their way to the main stable release. You can find all the releases in the releases page of the Kubernetes GitHub repository. Download the kubernetes.tar.gz file and extract it to find executables for all the Kubernetes components. The downloaded package, when extracted, has all the control plane components in it, all of them of the same version. Remember that there are other components within the control plane that do not have the same version numbers. The etcd cluster and core DNS servers have their own versions as they are separate projects. The release notes of each release provides information about the supported versions of externally dependent applications like etcd and core DNS. Check out the links for some references. That was a quick overview of the release versions. In the upcoming lecture, all the Kubernetes, the alpha and betas through a minor release. Critical bug fixes. Just like many other patch versions, while minor versions are released every few months with new features and functionalities, patches are released more often with critical bug fixes. Just like many other popular applications out there, Kubernetes follows a standard software release versioning procedure. Every few months, it comes out with new features and functionalities through a minor release. The first major version, 1.0, was released in July of 2015. As of this recording, the latest stable version is 1.13.0. Whatever we have seen here are stable releases of Kubernetes. Apart from these, you will also see alpha and beta releases. All the bug fixes and improvements first go into an alpha release tagged alpha. In this release, the features are disabled by default and may be buggy. Then from there, they make their way to beta release, where the code is well tested, the new features are enabled by default, and finally, they make their way to the main stable release. You can find all the releases in the releases page of the Kubernetes GitHub repository. Download the kubernetes.tar.gz file and extract it to find executables for all the Kubernetes components. The downloaded package, when extracted, has all the control plane components in it, all of them of the same version. Remember that there are other components within the control plane that do not have the same version numbers. The etcd cluster and core DNS servers have their own versions as they are separate projects. The release notes of each release provides information about the supported version. Hello and welcome to this lecture. In this lecture, we discuss about cluster upgrade process in Kubernetes. In the previous lecture, we saw how Kubernetes manages its software releases and how different components have their versions. We will keep dependency on external components like etcd and CoreDNS aside for now and focus on the core control plane components. Is it mandatory for all of these to have the same version? No, the components can be at different release versions. Since the Kube API server is the primary component in the control plane, and that is the component that all other components talk to, none of the other components should ever be at a version higher than the Kube API server. The controller manager and scheduler can be at one version lower. So if Kube API server was at X, controller managers and Kube schedulers can be at X-1, and the kubelet and kube proxy components can be at two versions lower, X-2. So if Kube API server was at 1.10, the controller manager and scheduler could be at 1.10 or 1.9, and the kubelet and kube proxy could be at 1.8. None of them could be at a version higher than the Kube API server, like 1.11. Now this is not the case with kube control. The kube control utility could be at 1.11, a version higher than the API server, 1.10, the same version as the API server, or at 1.9, a version lower than the API server. Now this permissible skew in versions allows us to carry out live upgrades. We can upgrade component by component if required. So when should you upgrade? Say you were at 1.10 and Kubernetes releases versions 1.11 and 1.12. At any time, Kubernetes supports only up to the recent 3 minor versions. So with 1.12 being the latest release, Kubernetes supports versions 1.12, 1.11 and 1.10. So when 1.13 is released, only versions 1.13, 1.12 and 1.11 are supported. Before the release of 1.13 would be a good time to upgrade your cluster to the next release. So how do we upgrade? Do we upgrade directly from 1.10 to 1.13? No. The recommended approach is to upgrade one minor version at a time. Version 1.10 to 1.11, then 1.11 to 1.12, and then 1.12 to 1.13. The upgrade process depends on how your cluster is set up. For example, if your cluster is a managed Kubernetes cluster deployed on cloud service providers like Google, for instance, Google Kubernetes Engine lets you upgrade your cluster easily with just a few clicks. If you deployed your cluster using tools like kubeadm, then the tool can help you plan and upgrade the cluster. If you deployed your cluster from scratch, then you manually upgrade the different components of the cluster yourself. In this lecture, we will look at the options by kubeadm. So you have a cluster with master and worker nodes, running in production, hosting pods, serving users. The nodes and components are at version 1.10. Upgrading a cluster involves two major steps. First, you upgrade your master nodes, and then upgrade the worker nodes. While the master is being upgraded, the control plane components such as the API server, scheduler, and controller managers go down briefly. The master going down does not mean your worker nodes and applications on the cluster are impacted. All workloads hosted on the worker nodes continue to serve users as normal. Since the master is down, all management functions are down. You cannot access the cluster using kube control or other Kubernetes API. You cannot deploy new applications or delete or modify existing ones. The controller managers don't function either. If a pod was to fail, a new pod won't be automatically created. But as long as the nodes and the pods are up, your applications should be up and users will not be impacted. Once the upgrade is complete and the cluster is back up, it should function normally. We now have the master and the master components at version 1.11 and the worker nodes at version 1.10. As we saw earlier, this is a supported configuration. it is now time to upgrade the worker nodes. There are different strategies available to upgrade the worker nodes. One is to upgrade all of them at once. But then your pods are down and users are no longer able to access the applications. Once the upgrade is complete, the nodes are back up, new pods are scheduled, and users can resume access. That's one strategy that requires downtime. The second strategy is to upgrade one node at a time. So going back to the state where we have our master upgraded and nodes waiting to be upgraded, we first upgrade the first node, where the workloads move to the second and third node and users are served from there. Once the first node is upgraded and back up, we then update the second node where the workloads are software until you finally have all new nodes with the new software version. Let us now see how it is done. Say we were to upgrade where you can easily provision new nodes and decommission old ones. Nodes with the newer software version can be added to the cluster, move the workload over to the new, and remove the old node, until you finally have all new nodes with the new software version. Let's end to $1. With kubeadm, run the current cluster versions, all kubeadm components. Once complete, your control. So the next step is to upgrade the kubelets. Remember, depending on your setup, you may or may not have kubelets running on your master node. In this case, the cluster deployed with kubeadm has kubelets on the master node, which are used to run the control plane components as pods on the master nodes. When we set up a Kubernetes cluster from scratch later during this course, we do not install kubelet on the master nodes. You will not see the master node. Get nodes command update the node configuration for the new kubelet version. Then restart the kubelet service. The node should now be up with the new software upgraded. Well, that's it for this lecture. Head over to the practice test where you will practice upgrading a live cluster.
In this video, I'm going to walk you through the
loop. Hello and welcome to this lecture on network policies. So let us first get our networking and security basics right. And I'm sorry if this is too basic, but I just wanted to spend a minute on this to make sure we're all on the same page before we begin. We will start with a simple example of a traffic flowing through a web, app, and database server. So you have a web server serving front-end to users, an app server serving back-end APIs, and a database server. The user sends in a request to the web server at port 80. The web server then sends a request to the API server at port 5000 in the backend. The API server then fetches data from the database server at port 3306 and then sends the data back to the user. A very simple setup. So there are two types of traffic here: ingress and egress. For example, for a web server, the incoming traffic from the users is an ingress traffic, and the outgoing request to the app server is egress traffic, and that is denoted by the straight arrow. When you define ingress and egress, remember you're only looking at the direction in which the traffic originated. The response back to the user, denoted by the dotted lines, do not really matter. Similarly, in case of the backend API server, it receives ingress traffic from the web server on port 5000 and has egress traffic to port 3306 to the database server. And from the database server's perspective, it receives ingress traffic on port 3306 from the API server. If we were to list the rules required to get this working, we would have an ingress rule that is required to accept HTTP traffic on port 80 on the web server, an egress rule to allow traffic from the web server to port 5000 on the API server, an ingress rule to accept traffic on port 5000 on the API server, and an egress rule to allow traffic to port 3306 on the database server. And finally, an ingress rule on the database server to accept traffic on port 3306. So that's the basic of traffic flow and rules. Let us now look at network security in Kubernetes. So we have a cluster with a set of nodes hosting a set of pods and services. Each node has an IP address, and so does each pod as well as service. One of the prerequisites for networking in Kubernetes is whatever solution you implement, the pods should be able to communicate with each other without having to configure any additional settings like routes. For example, in this network solution, all pods are on a virtual private network that spans across the nodes in the Kubernetes cluster, and they can all by default reach each other using the IPs or pod names or services configured for that purpose. Kubernetes is configured by default with an all-allow rule that allows traffic from any pod to any other pod or services within the cluster. Let us now bring back our earlier discussion and see how it fits into Kubernetes. For each component in the application, we deploy a pod, one for the front-end web server, for the API server, and one for the database. We create services to enable communication between the pods as well as to the end user. Based on what we discussed in the previous slide, by default, all the three pods can communicate with each other within the Kubernetes cluster. What if we do not want the front-end web server to be able to communicate with the database server directly? Say, for example, your security teams and audits require you to prevent that from happening. That is where you would implement a network policy to allow traffic to the DB server only from the API server. A network policy is another object in the Kubernetes namespace. Just like pods, replica sets, or services, you link a network policy to one or more pods. You can define rules within the network policy. In this case, I would say only allow ingress traffic from the API pod on port 3306. Once this policy is created, it blocks all other traffic to the pod and only allows traffic that matches the specified rule. Again, this is only applicable to the pod on which the network policy is applied. So how do you apply or link a network policy to a pod? We use the same technique that was used before to link replica sets or services to pods, labels and selectors. We label the pod and use the same labels on the port selector field in the network policy. And then we build our rule. Under policy types, specify whether the rule is to allow ingress or egress traffic or both. In our case, we only want to allow ingress traffic to the DB pod, so we add ingress. Next, we specify the ingress rule that allows traffic from the API pod, and you specify the API pod, again using labels and selectors, and finally the port to allow traffic on, which is 3306. Let us put all that together. We start with a blank object definition file, and as usual we have API version, kind, metadata, and spec. The API version is networking.k8s.io/v1. The kind is network policy. We will name the policy db-policy, and then under the spec section we will first move the pod selector to apply this policy to the DB pod. Then we will move the rule we created in the previous slide under it. And that's it. We have our first network policy ready.
Now, note that ingress or egress isolation only comes into effect if you have ingress or egress in the policy types. In this example, there's only ingress in the policy type, which means only ingress traffic is isolated and all egress traffic is unaffected, meaning the pod is able to make any egress calls and they're not blocked. So for an egress or ingress isolation to take place, note that you have to add them under the policy types as seen here. Otherwise, there is no isolation.
Run the kubectl create command to create the policy. Remember that network policies are enforced by the network solution implemented on Kubernetes cluster, and not all network solutions support network policies. A few of them that are supported are kuberouter, Calico, Romana, and WeaveNet. If you used Flannel as the networking solution, it does not support network policies as of this recording. Always refer to the network solutions documentation to see support for network policies. Also remember, even in a cluster configured with a solution that does not support network policies, you can still create the policies, but they will just not be enforced. You will not get an error message saying the network solution does not support network policies. Well, that's it for this lecture. Walk through the documentation and head over to the coding challenges to practice network policies.
This lecture, we will take a look at network policy.
Hello and welcome to this lecture. In this lecture, we will take a look at network policies in more detail. So here we have the same web API and database pods that we discussed about in the previous lecture. So first, let's be very clear with our requirements. Our goal is to protect the database pod so that it does not allow access from any other pod except the API pod and only on port 3306. So let's assume that we are not concerned about the web pod or the API pod. For those pods, we are okay for all traffic to go in and out from anywhere. However, we want to protect the database pod and only allow traffic from the API pod. So let's get the other things out of our way so we can focus exactly on the required tasks. So we don't need to worry about the web pod or its port, as we don't want to allow any traffic from any other sources other than the API pod. So let's get rid of that. We can also forget about the port on the API
pod to which the web server connects, as we don't care about that either. As we discussed, by default, Kubernetes allows all traffic from all pods to all destinations. So as the first step, we want to block out everything going in and out of the database pod. So we create a network policy. We will call it DB policy. And the first step is to associate this network policy with the pod that we want to protect. And we do that using labels and selectors. So we do that by adding a pod selector field with the match labels option, and by specifying the label on the DB pod, which happens to be set to role DB. And that associates the network policy with the database pod and blocks out all traffic. However, we need the API pod to be able to query the database on port 3306. So that's what we are going to configure next. First, we need to figure out what type of policies should be defined on this network policy object to meet our requirements. So there are two types of policies that we discussed in the previous lecture. We have ingress and egress. So do we need ingress or egress here, or both? So you always look at this from the DB pod's perspective. From the DB pod's perspective, we want to allow incoming traffic from the API pod. So that is incoming, so that is ingress. The API pod makes database queries and the database pods returns the results. So what about the results? Do you need a separate rule for the results to go back to the API pod? No, because once you allow incoming traffic, the response or reply to that traffic is allowed back automatically. We don't need a separate rule for that. So in this case, all we need is an ingress rule to allow traffic from the API pod to the database pod. And that would allow the API pod to connect to the database and run queries and also retrieve the result of the queries. So when deciding on what type of rule is to be created, you only need to be concerned about the direction in which the request originates, which is denoted by the straight line here. And you don't need to worry about the response, which is denoted by the dotted line. However, this rule does not mean that the database pod will be able to connect to the API pod or make calls to the API. Say, for example, the database pod tries to make an API call to the API pod, then that would not be allowed because that is now an egress traffic originating from the database pod and would require a specific egress rule to be defined. So I hope you get the difference between the two and are clear about ingress and egress rules. I just wanted to make sure that you're clear on what type of policy is to be selected for the requirement that you have in hand. So a single network policy can have an ingress type of rule, an egress type of rule, or both in cases where a pod wants to allow incoming connections as well as wants to make external calls. So for now, our use case only requires ingress policy types. Now that we have decided on the type of policy, the next step is to define the specifics of that policy. If it's ingress, we create a section called ingress within which we can specify multiple rules. Each rule has a from and ports fields. The from field defines the source of traffic that is allowed to pass through to the database pod. And here we would use a pod selector and provide the labels of the API pod like this. The ports field defines what port on the database pod is the traffic allowed to go to. In this case, it's 3306 with the TCP protocol. And that's it. This would create a policy that would block all traffic to the DB pod except for traffic from the API pod. Now, what if there are multiple API pods in the cluster with the same labels but in different namespaces? So say here we have different namespaces for dev, test, and prod environments, and we have the API pod with the same labels in each of these environments. The current policy would allow any pod in any namespace with matching labels to reach the database pod. We only want to allow the API pod in the prod namespace to reach the database pod. So how do we do that? For this, we add a new selector called as the namespace selector property along with the pod selector property. Under this, we use match labels again to provide a label set on the namespace. And you must remember that you must have this label set on the namespace first for this to work. So that's what the namespace selector does. It helps in defining from what namespace traffic is allowed to reach the database pod. Now, what if you only have the namespace selector and not the pod selector like this? In this case, all pods within the specified namespace will be allowed to reach the database pod, such as the web pod that we had earlier. But pods from outside this namespace won't be allowed to go through. Let's look at another use case. Say we have a backup server somewhere outside of the Kubernetes cluster, and we want to allow this server to connect to the database pod. Now, since this backup server is not deployed in our Kubernetes cluster, the pod selector and namespace selector fields that we use to define traffic from won't work because it's not a pod in the cluster. However, we know the IP address of the backup server, and that happens to be 192.168.5.10. We could configure a network policy to allow traffic originating from certain IP addresses. For this, we add a new type of from definition known as the IP block definition. IP block allows you to specify a range of IP addresses from which you could allow traffic to hit the database pod. So those are three supported selectors under the from section and ingress, and these are also applicable to the to section in egress, and we'll see that in a few minutes. We have pod selector to select pods by labels. We have namespace selector to select namespaces by label. Labels, and we have the IP block selector to select IP address ranges. These can be passed in separately as individual rules or together as part of a single rule. In this example, under the from section, we have two elements. So these are two rules. The first rule has the pod selector and the namespace selector together, and the second rule has the IP block selector. So this works like an OR operation. Traffic from sources meeting either of these criteria are allowed to pass through. However, within the first rule, we have two selectors part of it. That would mean traffic from sources must meet both of these criteria to pass through. So they have to be originating from pods with matching labels of API pod, and those pods must be in the prod namespace. So it works like an AND operation. Now, what if we were to separate them by adding a dash before the namespace selector like this? Now, they are two separate rules. So this would mean that traffic matching the first rule is allowed, that is, from any pod matching the label API pod in the same namespace, and traffic matching the second rule is allowed, which is from any pod within the pod namespace, that is either from the pod web, and of course along with the backup server, as we have the IP block specification as well. So now we have three separate rules, and almost traffic from anywhere is allowed to the DB pod. So a small change like that can have a big impact. So it's important to understand how you could put together these rules based on your requirements. So now let's get rid of all of that and go back to a basic set of rules, and we'll now look at egress. So say for example, instead of the backup server initiating a backup, say we have an agent on the DB pod that pushes backup to the backup server. In that case, the traffic is originating from the database pod to an external backup server. For this, we need to have egress rule defined. So we first add egress to the policy types, and then we add a new egress section to define the specifics of the policy. So instead of from, we now have to under egress. So that's the only difference. Under to, we could use any of the selectors such as a pod, a namespace, or an IP block selector. And in this case, since the database server is external, we use IP block selector and provide the CIDR block for the server. The port to which the requests are to be sent to is 80, so we specify 80 as the port. So this rule allows traffic originating from the database pod to an external backup server at the specified address. Well, that's it for now about network policies and rules. Head over to the lab and practice working with network policies yourself. I will see you in the next. In the next one.
demen ya? Saya dong. Toko umum ya? Không, tự nó trả về. Đúng rồi, chả sai gì cả. Đấy, nó phải chọc vào. Lỗi chịu.
Hello and welcome to this lecture. My name is Mumshad Manambat and we are going through the Kubernetes certification course. And in this lecture, we will discuss about ingress in Kubernetes. Before we proceed, please remember to subscribe to our channel so that you know when our new videos come out. We will start with a simple scenario. You are deploying an application on Kubernetes for a company that has an online store selling products. Your application would be available at, say, my-online-store.com. You build the application into a Docker image and deploy it on the Kubernetes cluster as a pod in a deployment. Your application needs a database, so you deploy a MySQL database as a pod and create a service of type cluster IP called MySQL service to make it accessible to our application. Your application is now working. To make the application accessible to the outside world, you create another service, this time of type node port, and make your application available on a high port on the nodes in the cluster. In this example, a port 38080 is allocated for the service. The users can now access your application using the URL http://IP of any of your nodes followed by port 38080. That setup works and users are able to access the application. Whenever traffic increases, we increase the number of replicas of the pod to handle the additional traffic, and the service takes care of splitting traffic between the pods. However, if you have deployed a production-grade application before, you know that there are many more things involved in addition to simply splitting the traffic between the pods. For example, we do not want the users to have to type in the IP address every time, so you configure your DNS server to point to the IP of the nodes. Your users can now access your application using the URL myonlinestore.com and port 38080. Now, you don't want your users to have to remember port number either. However, service node ports can only allocate high-numbered ports, which are greater than 30,000. So you then bring in an additional layer between the DNS server and your cluster, like a proxy server, that proxies requests on port 80 to port 38080 on your nodes. You then point your DNS to this server, and users can now access your application by simply visiting myonlinestore.com. Now this is if your application is hosted on-prem in your data center. Let's take a step back and see what you could do if you were on a public cloud environment like Google Cloud Platform. In that case, instead of creating a service of type node port for your where application, you could set it to type load balancer. When you do that, Kubernetes would still do everything that it has to do for a node port, which is to provision a high port for the service. But in addition to that, Kubernetes also sends a request to Google Cloud Platform to provision a network load balancer for this service. On receiving the request, GCP would then automatically deploy a load balancer configured to route traffic to the service ports on all nodes and return its information to Kubernetes. The load balancer has an external IP that can be provided to users to access the application. In this case, we set the DNS to point to this IP and users access the application using the URL myonlinestore.com. Perfect. Your company's business grows and you now have new services for your customers. For example, a video streaming service. Now you want your users to be able to access your new video streaming service by going to myonlinestore.com/watch. You'd like to make your old application accessible at myonlinestore.com/where. Your developers developed the new video streaming application as a completely different application, as it has nothing to do with the existing one. However, to share the cluster's resources, you deploy the new application as a separate deployment within the same cluster. You create a service called Video Service of type Load Balancer. Kubernetes provisions port 38282 for this service and also provisions a network load balancer on the cloud. The new load balancer has a new IP. Remember, you must pay for each of these load balancers, and having many such load balancers can inversely affect your cloud bill. So how do you direct traffic between each of these load balancers based on the URL that the user types in? You need yet another proxy or load balancer that can redirect traffic based on URLs to the different services. Every time you introduce a new service, you have to reconfigure the load balancer. And finally, you also need to enable SSL for your applications, so your users can access your application using HTTPS. Where do you configure that? It can be done at different levels, either at the application level itself, or at the load balancer level, or at the proxy server level. But which one? You don't want your developers to implement it in their applications, as they would do it in different ways. And it's an additional burden for them to develop additional code to handle that. You want it to be configured in one place with minimal maintenance. Now that's a lot of different configuration, and all of these becomes difficult to manage when your application scales. It requires involving different individuals in different teams. You need to configure your firewall rules for each new service, and it's expensive as well, as for each service, a new cloud-native load balancer needs to be provisioned. Wouldn't it be nice if you could manage all of that within the Kubernetes cluster and have all that configuration as just another Kubernetes definition file that lives along with the rest of your application deployment files? That's where Ingress comes in. Ingress helps your users access your application using a single externally accessible URL that you can configure to route traffic to different services within your cluster based on the URL path. At the same time, implement SSL security as well. Think of Ingress as a layer 7 load balancer built into the Kubernetes cluster that can be configured using native Kubernetes primitives, just like any other object that we've been working with in Kubernetes. Now remember, even with Ingress, you still need to expose it to make it accessible outside the cluster. So you still have to either publish it as a node port or with a cloud-native load balancer. But that is just a one-time configuration. Going forward, you're going to perform all your load balancing, auth, SSL, and URL-based routing configurations on the Ingress controller. So how does it work? What is it? Where is it? How can you see it? And how can you configure it? And how does it load balance? How does it implement SSL? Without Ingress, how would you do all of this? Well, I would use
That's only. Sao một cái break lát đi lại lại mà trời ơi. Nè này không đi kệ đi. Template nào. Quá buồn. Buồn vãi luôn đi. Trời ơi.
Let's look at how to configure the Docker daemon service. In the previous lecture, we saw how to manage the Docker service using the systemctl service management utility. We used the systemctl start command to start the Docker service, the status command to check the status of the service, and the stop command to stop the service. And note that this could be different on different operating systems depending on how you install Docker. In our case, we happen to be using Linux, and we happen to have the systemctl based service configuration. So configuring Docker as a service helps run the Docker daemon in the background and automatically starts the service when the system boots up. But you could also run Docker daemon directly as a foreground process using the dockerd command. So this is usually done for troubleshooting and debugging purposes, where if the Docker daemon is not starting up, you could run the Docker daemon this way and look at the logs and figure out what could be wrong. So this prints out the Docker daemon logs on screen, and to print additional details, use the debug flag along with the command. So this will now add more detailed information in the output along with the debug logs. So when the Docker daemon starts, it listens on an internal Unix socket at the path /var/run/docker.sock. This can be seen in the output of the logs. A Unix socket is an IPC or inter-process communication mechanism that is used for communication between different processes on the same host. This means that the Docker daemon is only accessible within the same host, and the Docker CLI is configured to interact with the Docker daemon on this socket. Now, what if we need to establish connectivity to the Docker daemon from outside of this host? Now, say there is another host with the Docker CLI installed on it, and we want to target the Docker host to run containers. So let's say the Docker host is a server somewhere hosted somewhere in your infrastructure, and this host here is your laptop, right? So you have Docker CLI installed on your laptop, and from your laptop you want to run Docker commands that can target this Docker host. So as of now, with the current way things are set up, the default way, the Docker daemon is not accessible outside of the Docker host because it's only listening on the Unix socket. So we could make the Docker daemon listen on a TCP interface on the Docker host by adding the host option while running the Docker daemon command like this. In this case, our host happens to have an interface at 192.168.1.10, and the standard port for Docker happens to be 2375. Now, the Docker daemon is accessible from outside of the Docker host using the IP 192.168.1.10 and the port 2375. The other host can now target the Docker daemon using the Docker commands by first setting an environment variable called docker_host to point to the IP address of the Docker host. Now remember that there is a reason why this is disabled by default. You must be extremely careful before making your Docker API server available on an interface on your host, especially if your host is on the internet. This will allow anyone on the internet to run containers on this host, because the default setting of Docker, if you make it available on a public interface, it's not encrypted and it's not there's no authentication required, right? So that's the default setting. So if you do this, then you have to be extremely careful, and you should not do this on a public-facing host. So there have been numerous occurrences of hacks where people try to connect to your Docker host using the port 2375 and try and run containers for Bitcoin mining and things like that. So if you are allowing external access, you must also take care of security. Now, by default, as I said, the Docker daemon serves unencrypted traffic. To enable encryption, you must first create a pair of TLS certificates and add the TLS flag to true and pass in the path to the certificate and key like this. So with TLS enabled, the standard port is now 2376 instead of 2375. 2375 is for unencrypted traffic and 2376 is for encrypted traffic. So keep that in mind. Now, as of now, we have all the options specified while running the dockerd command as options in the command line. Now, these options could be moved to a configuration file at the location /etc/docker/daemon.json. This is the default configuration file. The file is in a JSON format. This is not created by default, so you must create one if it does not already exist. Specify the options here in a key value format. Now note that the host's property is an array that supports multiple listeners, so it has to be specified like this. Once this file is configured, we no longer have to pass in the parameters in the dockerd command. Now, if you do happen to specify a flag both in the daemon.json file and in the command line, then the service throws an error that says that there's a conflict on an option, also known as a directive, between the value specified in the configuration file and the daemon.json file. So in this case, on the command line, we set the value of debug to false, but in the daemon.json file, it's set to true. So it's failing, and because those two are different. This configuration file is also read and the values are interpreted when we run Docker as a service using the systemctl start command. So the options are passed through. Well, that's it for this lecture, and I will see you in the next.
Let's look at how. Start by looking at securing the Docker daemon itself. First of all, what is the problem if someone gains access to the Docker daemon? Anyone with access to the Docker daemon can delete existing containers hosting applications and thereby impacting your users. If you happen to have stored your application data in the form of Docker volumes, then the person with access to the Docker daemon or the Docker API can delete volumes and resulting in a data loss situation. Anyone with access to the Docker daemon can run containers to run their own applications, say for example for Bitcoin mining purposes. Anyone with access to the Docker daemon can gain root access to the host system itself by running a privileged container. We'll look at what a privileged container is in a bit. And once they gain access, gain root access to the host system, they can target other systems in the environment and the whole network infrastructure itself. So earlier, when we talked about configuring the Docker daemon, we discussed about the different access methods. We said that by default, Docker exposes the Docker daemon service within the host only on a Unix socket, and this prevents anyone outside of the host from accessing the Docker daemon. And that's why this is set to that option by default. Now note that we're talking about the Docker daemon service itself and not the applications deployed by Docker. The applications deployed can still be accessed as long as we publish ports on those applications on the hosts. Here, we're referring to the Docker engine, the Docker API server itself. So as of now, only someone who is logged in to this host has access to the Docker service. So the first level of security that we must think about is securing the Docker host itself from unwanted access. Now, as you would secure any server, you must secure the Docker host with the usual security best practices of securing a server, such as disabling root users, controlling who has access to the server, disabling password-based authentication, strictly enforcing SSH key-based authentication, disabling any unused ports, etc. We also discussed about configuring external access to the Docker daemon. So at times, you may really have to allow access to the Docker daemon from another management host, or say a user's laptop, or for integration purposes with other tools. Now this must be done only if it's absolutely necessary. So for this, we add the hosts option to the daemon.json file. And that now enables access to the Docker daemon from outside of the Docker host itself through an interface on our host. Now, if you have to do this, make sure you expose the Docker daemon on interfaces that are private and only accessible from within your organization. So if your host has a public facing interface, then make sure the daemon is not exposed on those interfaces. By allowing external access, we must also secure communication with TLS certificates. So for this, we configure a certificate authority, CA, and create CA certificates for the server. We will call it server.pem and serverkey.pem. And we place these on the Docker host and configure the daemon.json file and configure the daemon.json file to read them, along with setting the TLS option to true. The port is now 2376 instead of 2375. So with this, anyone outside of the Docker host can access the Docker API and target it with the Docker commands by simply setting the Docker host environment variable to point to this host. With encryption enabled, you must set the TLS flag to initiate secure connection. For this, set the Docker TLS environment variable to true. Now note that any of these environment variables being set can also be passed in as a command line parameter like this. But since we have already set the environment variable, we don't need it, so we will get rid of it. So with this setup, the Docker CLI on the Docker client and the Docker server starts communicating in an encrypted manner. However, there is still no authentication, meaning anyone who knows that the Docker daemon is being exposed on port 2376 on this host can still access our Docker daemon by simply setting the Docker TLS environment variable to true and pointing the Docker host environment variable to our host. And they can start deploying containers on our host or delete existing containers. So the next step is to enable certificate-based authentication. For this, we copy the CA-cert to the Docker daemon server side and configure a TLS CA-cert parameter in the daemon.json file along with the TLS verify flag to true. The TLS verify flag is what enables authentication, and the CA-cert will be used to verify certificates of clients when they send them. So our clients now need certificates signed by the CA, and that's the only way now they can access the Docker daemon. So we generate certificates for our clients called client.pem and clientkey.pem and share that securely with the client server that wants to connect to the host, along with the CA-cert, the certificate of the CA. On the client side, we set the Docker TLS verify flag to true instead of the TLS flag we set earlier, and then we either pass in the client certificate through the command line parameter, or we drop the certificate into the .docker directory under the user's home directory. From there, the Docker command will automatically pick up these certificates. And now, only clients with signed certificates from the CA server can access the Docker daemon. So remember, the TLS option alone does not authenticate, it only enables encryption, and anyone can still access the Docker daemon with the TLS flag enabled. The TLS verify option is what enables authentication. So to summarize, without authentication and just to enable encryption, we configure the TLS flag and the TLS certificate and key flag on the server, and on the client side we just set the TLS flag to true. This can either be set on the command line as the --TLS option or an environment variable called docker_TLS. With authentication, on the server side, we set the TLS verify flag along with the server certificate and key and the CA certificate as well. And on the client side, we set the TLS verify flag to true along with the TLS certificate, TLS key, and TLS CA certificate passed in either as command line parameter or environment variable, or placed in the .docker directory under the user's home directory. Well, that's it for now, and I will see you in the next one.